Okay, let's unpack this. Imagine you've got a really complex 3D shape, maybe a high-tech pressure vessel, and your mission, right, is to wrap it perfectly, like millimeter by millimeter, with these composite fibers. How do you actually ensure every single bit is covered just right, that the material is distributed flawlessly? Today, we're diving deep into, well, the fascinating world of composite pressure vessel manufacturing. Specifically, we're looking at this really crucial step called correction within the WinderCAM system. It feels like this is exactly where, the theoretical design meets the nitty-gritty of manufacturing reality.
That's absolutely spot on. And our mission here in this deep dive is really to show you how these incredibly precise computer-aided tools work. They don't just design these components. They actively ensure you get full surface coverage and genuinely homogeneous distribution of material.
Got it.
Even when you're tackling really tricky geometries, yeah, we're going to uncover the clever methods that will literally bridge that gap between what the engineers dream up on paper and what the machines can actually build perfectly.
Okay, so let's get right to the heart of it then, this correction step. What's the absolute, like the non-negotiable goal this part of WinderCAM is trying to hit every single time?
Right. The fundamental goal, it's crystal clear. Complete, full surface coverage of the mandrel, that's the form you wind on for these composite pressure vessels. And critically, ensuring a homogeneous distribution of material. Think ultimate uniformity, in every fiber placement. Now, what's really interesting if we zoom out a bit is the path the fiber takes. Winding along the absolute shortest path on a curved surface, that's what we call a geodesic path, that's often ideal for structural stability. Makes sense, right? But it's not always feasible. Sometimes it's just not possible to rely only on that geodesic path. This comes up especially with certain vessel shapes or maybe when you're just trying to create smooth, continuous winding trajectories.
Yeah, I can picture that. Trying to wrap something perfectly around, say, a really tight curve. I can almost see the fiber getting like stuck on what you called a singularity, a point where the material just can't decide which way to go, like trying to wrap string neatly right over the pointy tip of a cone without it bunching up, or maybe just, can't smoothly transition to the next winding circuit. That sounds like a quality control nightmare. So what's the actual, the trick, the innovation that solves this near those tricky endones or poles?
Ah, okay, that's where controlled friction enters the picture. Near those end domes, those polar regions, we actually intentionally introduce a very precise amount of friction between the fiber and the surface. And this friction lets us create paths that deviate slightly, that are not perfectly geodesic. And here's the really crucial part. The winding angle as it passes the edge of that polar opening, the periphery, it must become exactly 90 degrees, perpendicular. This tangential placement, as we call it, isn't just like a nice to have, it's the absolute key, the secret sauce to keeping that winding process continuous and moving seamlessly to the next circuit. It ensures the material always lays down exactly where it needs to.
Okay, that makes perfect sense. You're essentially forcing the material to behave in a very specific, very controlled way right where it matters most. And this leads us neatly into what you mentioned before, the winding pattern. What exactly is that? Is it like a blueprint?
Yeah, you call it a blueprint. A winding pattern is essentially a repeatable set of instructions. It's like a precise recipe for laying down the fibers. The goal is always uniform coverage, especially on these rotationally symmetric vessels. So it's about figuring out the best arrangement of windings and their paths, sort of simultaneously. The system's objective, then, is to find patterns that don't just give you that perfect coverage, but also minimize any excess windings. You don't want more circuits than the structural analysis originally called for. Because, let's face it, every extra wrap adds material, it adds weight, it adds cost, so efficiency is absolutely key here.
Right, so it's like the ultimate cheat sheet for fiber placement, making sure you don't end up with something that looks like, I don't know, a badly wrapped Christmas present. Okay, now let's walk through the WinderCAM correction tab interface itself. This is where you actually see these tools in action, right? What hits you first?
Yeah, exactly. So right near the top, you'll likely see a parameter. Internally, it's often referred to as convenience. It's a bit of an unusual spelling, perhaps, but what it represents is essentially how many distinct segments or partitions the vessel's circumference is conceptually divided into by those winding paths. It's really crucial because it defines how the pattern repeats itself spatially around the object. It visually gives you a sense of these gussets or sections as the fibers are laid down.
Okay, convenience parameter. Got it. And right next to that, I think you mentioned a table for pattern selection. This isn't just a simple list, is it?
Oh, far from it. That table, it's actually the powerful result of an automated, very systematic search the software performs. What it does is explore a huge range of possibilities, different fiber properties like the width of the roving, which is that bundle of fibers, and also various friction levels. It calculates all the acceptable combinations of these pattern characteristics.
Mm.
So the table then presents these successful combinations back to you. It shows, for instance, the resulting number of complete layers that will be formed by a given pattern. This is, well, tremendously helpful. It guides you in choosing patterns that really align best with your manufacturing needs. Things like ensuring you get a whole number of overwound layers and, importantly, minimizing any unnecessary windings.
Makes sense. And then below that table, there's that circular diagram you talked about, showing the layout with winding numbers. That sounds like a really vital visual check.
It truly is. That diagram gives you this really powerful visual snapshot of how a chosen winding pattern will actually look in your specific vessel. It graphically shows how each winding circuit propagates, how it moves around the mandrel's equator, and the winding numbers, they clarify the exact sequence, the order in which those rovings are placed. This visualization is just essential for quickly assessing, does this pattern genuinely lead to homogeneous coverage? And do we get the required overlap for multiple layers without leaving any gaps, or conversely, using way too much material? It's like a quick visual health check for your winding design.
Okay, brilliant. And finally, the big button, correct coil. This sounds like the ultimate fine-tuning mechanism. What's it actually doing when you click that?
Right, this button kicks off what we call a refinement procedure. And here's where it gets really quite clever. See, it's actually quite rare for the angular propagation that's generated by the actual fiber path. That's, how much the fiber naturally spreads or turns around the vessel as it lays down. It's rare for that to perfectly, exactly match the angular propagation required by the ideal theoretical winding pattern you selected. So this button triggers a sophisticated fine-tuning process to achieve that perfect match.
Huh. So how does this refinement magic actually happen? Is it physically adjusting the machine, or is it more about recalculating the parameters again?
It primarily works in two main ways. One way is it can involve applying a tiny, almost imperceptible additional turn right at the polar areas. We're talking usually on the order of just 1/10 of a degree, maybe less, just to slightly enlarge the total turning angle of a complete circuit. Or, and this is often more powerful, it can perform a highly refined, targeted search. It looks very closely around the material properties and friction settings you've already chosen to pinpoint the exact values that will ensure the fiber path's actual angular propagation and the pattern's required angular propagation become identical. And the beauty of it is, this whole procedure is automated. It's fast, it's pretty straightforward, and incredibly reliable. It gives you this comprehensive range of data so you can select the truly optimal patterns for your manufacturing needs. Basically, yeah, it takes the guesswork out of achieving that precision.
Wow. So, okay, really this correction step. It isn't just some minor tweak at the end. It's more like the critical handshake, isn't it? Between the theoretical design and the hard realities of the factory floor, making sure both precision and efficiency are met.
Absolutely, you've nailed it. It's a sophisticated and honestly a truly critical part of the entire design to manufacturing process. It effectively bridges that gap between what's theoretically perfect for structural integrity and what's practically manufacturable. And ultimately, that leads to a far more optimal, more robust design for these composite pressure vessels.
So essentially what we've unpacked today is how a system like WinderCAM really empowers manufacturers. It lets them take a theoretically perfect design and actually make it a tangible reality, ensuring precision, coverage, and efficiency in, every single fiber laid down. It's about turning those abstract ideas into concrete, high-performance products.
Exactly. The correction step perfectly highlights how advanced engineering marries those intricate, tiny details with the bigger picture of manufacturability. It ensures that every layer, every single fiber, contributes optimally to a reliable final product.
And that kind of leaves us with a final thought for you, our listener, to ponder. In what other complex design or manufacturing processes out there do you think a similar correction or refinement step might be absolutely critical, to bridge that often tricky gap between ideal theory and real-world application? Something to think about?